So, welcome back. We are continuing our study of first order logic. We have gone through the syntax, the semantics, and we have looked at two proof algorithms, forward chaining or data driven algorithm and backward chaining or goal driven algorithm. Both the algorithms are quite interesting and we are not done with them yet. We will come back to see how forward chaining can be made more interesting, and also we will come back and check how backward chaining can be used to implement a language like Prolog, which is a style of logic programming language, which basically says that you can use logical reasoning for computation. So, we will come to that later, but we have one issue to address before we do all that one, and that is that both forward chaining and backward chaining were not complete, and we did that by showing an example that in which they could not find the proof. We will start with that example and then we will introduce this method called the resolution refutation method, which has been shown to be complete for first order logic. So, this is the example that we had closed with last time. This is just a recap, and you remember that we had this knowledge base which had these 4 formulas whose symbols we had not at that moment clarified, but here we have said that O stands for on. In one of the interpretations that we saw, O stands for on, M stands for maroon, and the 3 symbols, constant symbols A, B, C stand for block. And the knowledge base said the following, that A is on B, B is on C, A is not maroon, C is maroon, but we do not know, we did not say anything about the color of B, maybe we do not know. Okay. We saw that another interpretation of the same knowledge base, which is given on the top, those 4 formulas could be in terms of people, and then O could be looking at, it is a binary relation or binary predicate, M is married, which is a unary predicate, and 3 constant symbols, they stood for 3 people essentially. And then we saw that what that same knowledge base can be interpreted as is that Betty is looking at Cuthbert, Archie is looking at Betty, Archie is not married, Cuthbert is married, and we did not know about Betty, because it is the same knowledge base, we do not know about that middle element as to whether the property of M, which in this case happens to be married, is there or not essentially. So, that was what has been given to us. The question we had was whether there exists 2 elements out of A, B and C, because that is our domain has only 3 elements. So, there exists an x and there exists a y such that O x y is true, not M x is true and M y is true. So, in the interpretations that we saw, in one world we are asking, is there a non-maroon block on a maroon block? Remember, the middle block we did not know whether it was maroon or not. And in the people's world we said, is a non-married person looking at a married one essentially. Again, we did not know about one of them, whether that person was married or not essentially. And then I had asked you to think about this, that this is clearly true, that the answer is yes essentially. And we can discuss the answer, it can be in 2 cases. So, if the middle block, which is A, B, C, A, B is the middle block, there are 2 cases, B is can be maroon or B can be not maroon. If B is maroon, then because A is on B, the statement is true. If B is not maroon, then because B is on C, the statement is true. So, in one of each of those 2 cases, the statement is true, but we still do not know what is the color of B, and we do not know as to which non-maroon block is sitting on which maroon block. What we do know, what we can infer using logic is that some non-maroon block is sitting on some maroon block, even though we do not know which one. And then we had said that forward chaining and backward chaining are incomplete neither of them is able to generate a proof of the statement that we have, the goal that we have. And we had said that we will look at this method called the resolution refutation method, which is both sound and complete for first order logic. So, it is a very useful method to have around. So, let us look at that method first. As usual, let us begin with propositional logic. It is a simple logic, and some of the ideas that we want to discuss can be discussed more easily here before we apply them to first order logic. And the resolution method requires that the formula is in conjunctive normal form, or CNF as it is popularly known. We say that a formula f is in conjunctive normal form if it has the following structure, that the formula is a set of sub formulas joined together by AND. So, C1 and C2 and C3 up to Cn. It can, let us say there are n formulas. Each Ci is called a clause, and each clause is a disjunct of literals. So, each Ci is a formula in which di1, di2, di up to dik are joined together using the OR connective, and inside the clause the only connective is OR, that is this thing. Each literal, each di is either a proposition or an atomic formula or the negation of a proposition atomic formula. So, this structure of formula is called CNF, and you can observe that the set of connectives that we are using are the three that I had said are popular, and or and not. So, we are using these three sets. At the highest level we are using and, at the as we go nested inside the formula, inside the nested formula we use or, and at the innermost level is the negation, and negation is only applied to atomic formulas. So, this is the only place where negation is applied. You can't say negation of A and B and that kind of stuff. We will often write this as a set also, many books do that. So, that formula is a set. So, this and this comma here is like an and the comma at the next level of nested net is an OR essentially, and of course, the negation will be there somewhere inside there. So, it is like a set of sets, the first subset and the second subset, and so this is the sentences in the knowledge base. Now, it can be shown that any formula can be converted into CNF, because otherwise it would not be useful. We have already said that we can express any formula that we want using the three connectives and or not, but now we are saying something more, is that not only that, you can also rearrange the formula so that it is in conjunctive normal form, which is a set of clauses, and each clause is a disjunct of certain literals essentially. Now, this conversion generally results in an increase in the size of the formula. Now, generally conversion into CNF results in the increase in the size of the formula, and that is important because whenever we are writing programs, we often measure complexity in terms of length of the input, and the length of the input, if it is increasing in this process, that means our programs for generating proofs will also be more expensive. Sometimes it can reach even exponential number of clauses. How do we do this conversion? We basically use this set of substitution rules that we have discussed: associativity, distributivity, contrapositive, implication, De Morgan's laws. Some application of these rules, we can convert this into any formula into CNF. So, I will leave you to think about this. I am sure you have studied this somewhere essentially. So, what is the resolution rule? Okay. So, that is a new rule of inference that we are looking at, apart from the rules that we had seen earlier, and it was shown by Robinson, who invented the resolution method, and it was quite recent in 1965, that this rule is enough to make all the inferences that you need to make essentially. And what does the rule say? The rule says that if the first clause contains a literal q, and if the second clause contains the literal not q, then in the resultant clause you take the rest of the literals in from each clauses and put them together to form a new clause essentially. So, you can see that the thinking about formulas as sets also helps essentially. So, from this set you remove q, from this set you remove minus not q, and then you take the union of the other two sets essentially. Now, of course, this does not look very useful at this moment, but eventually we will see that this works in reducing our formula sufficiently to what is called a null clause. I am jumping the gun here, but let us see essentially. So, this rule is enough to prove that what you wanted to prove is true. For a smaller formula from R or Q, from P or not Q, we eliminate Q and not Q, and we are left with R or P essentially. More interestingly, if we had something like this, if we had R or Q and if we had not Q here, we would reduce it to R essentially. So, you can see glimpses of other rules in the resolution rule as well. It is a general enough rule to subsume most other rules. Is this rule a valid or sound rule? We have already seen how to do that. In this case, it suffices to show that this formula that I have written here is a tautology. What is this formula? This formula is the antecedents connected by an and on the right hand side are those same antecedents plus the new formula which is the resolvent essentially R or P. And if you show that this is a tautology, that means that if you started with the left hand side here, which is R or Q and P or not Q, and you ended up with the right hand side, which is what you would do by adding this new clause to that, then they are logically equivalent essentially. And we will exploit that fact essentially. Now, you might remember the deduction theorem. It said that given a set of premises alpha 1, alpha 2 up to alpha n and the desired goal beta, we want to determine if the formula alpha 1, alpha 2, alpha n whole thing implies beta is true or not. This follows from the deduction theorem, which said that if the premises entail the conclusion, then this formula should be a tautology. It is entailed by nothing, there are no premises for that essentially. And that is a principle that we are going to use again. We use it for the tableau method, and something similar what we will be doing here as well. Also observe that this formula is a tautology if you add a negation sign before that, then that formula will become a unsatisfiable formula. We have already seen that the negation of a tautology is unsatisfiable or a contradiction essentially. We are going to follow again the proof by contradiction. We had said that there are two methods which use proof by contradiction, the tableau method and the resolution method, and we are going to do that again essentially. So, we want to show, we are going to take the formula that we want to show to be a tautology, add a negation sign before that, and then we would want to show that that is unsatisfiable, because it was shown by Robinson that the method is a refutation method, that it is complete if you want to show that a set of clauses is unsatisfiable essentially. So, that is what we are doing. We are basically eliminating the implication from this here. If you want to show that alpha 1 and alpha 2 up to alpha n implies beta, then we can push that not inside and replace implication by not and or. So, this implication has been replaced by this not and this or, and once we put the not again inside, then you can see that what you get is the original formula plus the negation of the goal essentially. So, we have a formula which is in CNF form, assuming alpha 1, alpha 2 and alpha n are in that form. So, if this set of clauses is unsatisfiable, then so is the original formula that we started with, which means that original formula without the negation is a tautology, and that is what we want to show. What does the resolution refutation do? It does the same thing. There is a little bit of repetition in these slides here. So, you will have to bear with me. Show that this formula is unsatisfiable. We convert it into CNF, the form that is required by the resolution method, and we make sure that the final form of the formula, which is in the last line shown here, A alpha 1 prime, alpha 2 prime and so on, that they must conform to the CNF structure. We may need to convert each of the premises and the negated goal into clause form denoted by alpha 1 prime and beta prime essentially. So, alpha 1 itself could have other connectives, but eventually we want to reduce the input knowledge base, which is going from alpha 1 up to alpha n, it should be in clause form. I am using the term clause form, which is just another name that we often use for CNF, because it is a set of clauses essentially. So, what is the basic algorithm for doing resolution? Given a set of clauses, pick any two clauses and add the resolvent to the set. Which two clauses? At some point we will try to discuss that, but basically our goal would be to add smaller and smaller clauses as we will see, and we will look for strategies which do that essentially. If at any time we generate a resolvent that is an empty clause, which means it is nothing. How can we generate an empty clause? We could generate it if we had P, and if we had not P, then we would generate the empty clause. We often denote the empty clause by a box, if we are using the graphical notation. And the empty clause is known to evaluate to false. So, what does that mean? It means that we have reduced the formula to a contradiction, or we have shown that our formula is a contradiction, and that is why the method is called the refutation method, that you add the negation of the goal and then show that it leads to a contradiction. So, as I said above, an empty clause can be generated from two clauses, let us say S and not S, by the application of the resolution rule. And if the conjunctive formula has both S and not S, remember it is in CNF form, then it must be false essentially. So, to show that a formula is unsatisfiable, let the original formula be P 1, P 2, P n, that is what we want to show to be unsatisfiable. It is a conjunction of n clauses. To this we add a sequence of resolvents R 1, R 2, R 3. Each resolvent is obtained by taking two clauses from our knowledge base and adding the resolvent to that. How do we pick two clauses? Two clauses, one of which has a positive literal and the other one has that same negative literal essentially, and then we can remove that literal from there. The database at all stages will be logically equivalent, because the resolution rule is sound, and I hope that you would have shown that the formula that we had was a tautology. So, this is what is happening. You start with P 1, P 2 up to P n, then you add R 1, then you add R 2, then you add R 3, and you keep doing that till you add the null clause to the formula essentially. Now, since the last set of clauses evaluates to false, why does it evaluate to false? Because remember that this is like a conjunctive formula, P 1 and P 2 and so on. These are clauses. So, inside they may have some disjunctions, but there is an and connecting all of them, and when you say something and false, it must be false. So, if you draw the truth table for alpha and false, you can show that this is false, because false by definition is false. So, the value of alpha does not affect this. So, if you can add the null clause to your set, then you have shown that the original set, which is P 1 up to P n, must be unsatisfiable essentially. Okay. So, essentially if you are writing a program to do this, your strategy to select clauses must be to eventually go, as I said, to go towards smaller and smaller and smaller clauses. And if one of the clauses is a unit clause, which means it has only one disjunct, then you can see that if you start with a formula of length 4, you will reduce it to a formula of length 3. Then if you find another unit clause somewhere, then it will become length 2, and then so on and so forth. Eventually, if it is length 1 and you find its negative literal somewhere, then you have brought it down to length 0. So, one of the strategies that people use is to prefer unit clauses essentially, but maybe we will mention strategies explicitly at a later point of time. So, this is a resolution refutation method. It was devised by Alan Robinson in 1965. He showed that the resolution refutation method is complete for deriving the null clause essentially. A proof by resolution method is a proof by contradiction. We have already said that. We start with a set of premises, negate the goal and add it as another clause, and show that it leads to a contradiction, something that is false or not possible. If the input formula is unsatisfiable, then Robinson showed that there always exists derivation of the null clause essentially, which is of course comforting. Next, we will look at some examples. So, we will start with our Alice problem, but let us do that after a break, when we should look at some more examples together. So, we will see you after a short